Good morning. This is segment number 1 for section 7.1. And just real briefly, I know that these sections come what looks to be out of order from the textbook, which is intentional. The idea here being that the way that this textbook normally plays out, it goes through right triangles, how to solve them, some applications, then moves directly into circles. Then does a bunch of other sorts of things that have nothing to do with any kind of practical geometry. And then at the end, it goes through chapter 4, 5, and 6, and then it comes back to chapter 7, where it starts to solve non-right triangles, which seems very unnatural to me to do it in that order. So rather than delay the entire semester to talk about triangles that aren't right, I insert this here kind of halfway through the second course unit. So here's the basic idea. What we know how to do now is solve any right triangle, provided that we have certain pieces of information. And one of the pieces of information we always know about a right triangle is that one of the angles is right. So the different scenarios we've looked at is where we have one angle and one additional angle, right? So we have one right angle and then one of the acute angles, which automatically gives us the third angle because of the sum of the interior angles. And then we need one side. So that was the first example we did of solving a right triangle. And then the alternative is to have two sides. And with two sides, we can then employ the Pythagorean theorem to find the third side and use a basic trig function to find the two acute angles. So those are kind of the minimum pieces. We need three pieces of the triangle, one of which is always an angle. Now, it turns out that is maybe not the best we can do. We can actually do a little bit better. So let me kind of diagram where we're going to be in terms of these next three sections, so that you have something to kind of sort of think about. The biggest thing when trying to solve triangles that are not oblique, that are not right, that is to say oblique triangles, is that you have to sort of right from the beginning figure out what the setup is. What is it that you know, and then you choose a method to get there. So let me just start here a second, and I'll diagram what I'm talking about. So section 7.1, page 1. So when we talked about congruence arguments, we said you can show that two triangles are congruent, and here's 4 different ways that works. Here's one way that sometimes works that we sort of alluded to, and then there's one way that doesn't. Then there's one way that it brings about similarity. So as you recall, we had a couple methods that involved where you have two angles and a side. So either we had angle, side, angle, where we had and I drew some diagrams. I won't repeat it. But you have two angles and one side that's between them. Then you have angle side, where you had two angles and then a side that's not between those two angles. Then you had the sort of screwball one, where we said this doesn't always give you a unique answer, but it can give you up to 2 answers, or maybe none, depending on the scenario, side angle, where we have two sides, doesn't really matter their position, and then one angle. And then we had what we called side angle side, where instead of having 2 angles and an included side, we instead have 2 sides and an included angle. And then finally we had side, where we have all 3 sides. And we said that if any of these conditions, with the exception of this one, if any of these other 4 exist, then you have then two triangles must be exactly identical in a number of ways, right? They have the same measure of corresponding angles, measure of corresponding sides, their areas are the same, etc. So the one that's a little bit tricky is this one, where you can end up with possibly two different combinations of triangles, but there is a relationship between the two. And then you had, of course, angle, which is just similarity and doesn't give you anything. Okay, so this is sort of the breakdown. If 2 triangles are congruent, that means that there's the combination of whatever combination you have creates a unique situation where that's the only triangle that can have that property. And so therefore that leads to a process by which we can solve these triangles. Okay, so for oblique triangles, meaning ones that are not right, even though it works for right triangles, but typically you're using this for triangles that are not right. If you have these two situations here, then you use the law of sines, something called the so-called law of sines, and we'll derive that here in a minute. So law of sines, and we will do this in section 7.1. Now, this one actually also uses the law of sines, but we have some special criteria. We have to go in and check and say, well, is it a triangle that can exist? Is it a situation where there's only one triangle? Is it a situation where there's possibly two triangles? And once we decide which one it is, then we can go in and solve, maybe either for both or one, or not have to solve anything at all. This is what's called the ambiguous case of the law of sines. Okay, and that is in 7.2. And we'll treat that as a separate sort of situation. And then finally, you have these other two combinations, which we will use the so-called law of cosines. And we will derive that as well in a similar way to the way we derive the law of sines, but this is all in section 7.3. So when you're approached with a triangle, an oblique triangle that you need to solve, the first thing you need to do is decide which one of these three types is it. Is it two angles and a side? Is it, do we have an included angle between two sides, or is it a non-included angle with two sides known? Is it side, side, side? And once you can decide which kind this is, then you know which method to use. And this is the issue, is that this actually is computationally more challenging, the law of cosines. And there is a tendency for people to want to flip between them, and that can cause major problems. But we'll get to that at a later point. So for 7.1, we are going to use exclusively the law of sines. So anything that has a triangle that has two angles, period, it's going to use the law of sines. So let's develop the law of sines. First off, I want to do a quick derivation. And what this is going to do is it's going to involve determining the area of a triangle and then using that as the basis to create this formula that we have. So, okay, so let's start with this idea. Let's have a triangle, and it doesn't necessarily have to be an acute triangle, but we'll start with, we'll use one that looks acute. And we've got, let's make some labels here, A, B, C, and then opposing sides, A, B, C. All right, now, if we would like to figure out the area, and I think that previously in some of our derivations, we said, that the area of a right triangle is one half the product of the legs. 1/2 times the product of the legs. And it's easy enough to show that it's true that your 1/2 base times height is actually a good formula for any triangle, because you just simply split it in such a way that you have a right angle. Now you have two right triangles, and then this area plus that area equals the same, and you end up with exactly the same result. It's not a great, it's not a very challenging proof, but regardless, let's kind of put that h in there. Now that generally is called the altitude of a triangle, the height of a triangle. And if we were to calculate the area of this triangle, we would say, well, that's 1/2 base times height, and I set it up so that B is actually the base. So then the question becomes, well, do we really need h? Can we use one of these trig functions to maybe replace it? And the answer is, of course, yes. So thinking about the sine of angle A, sine of angle A is equal to the opposite. If we were looking at this triangle here, it's the opposite over the hypotenuse, which is simply h over c. And then if we solve for h, H is just simply equal to C times the sine of A. Okay, so what that gives us is we kind of replace, we get rid of the height and we have it in terms of a trig function. So the area of a triangle is equal to 1/2 B times C times sine of A, or at least that's one way to formulate it. Now we could just as easily do this from the other side and say, well, instead of using angle A, what if I use angle C? And what you would come up with is, alternatively, you would have the area is equal to 1/2 A times B times sine of C, right? Which is the same area, it's the same triangle. Now you would have to create a different altitude, but you could certainly do that by simply, starting rotating the triangle or something, or thinking about it and having, a perpendicular drop down this line, and you would end up with a very similar formula that says the area is equal to 1/2 A times C times the sine of B. And like I said, you couldn't necessarily use this diagram, but that's what you come up with. So note, all of these sort of have a rotation to them, right? You have the angle and its two closest sides, angle and its two closest sides, angle and its two closest sides. That's not really particularly relevant, but I mean, if you want to quickly find the area of a triangle, you need side, angle, side, or a way to find it. But the net result is, if I then take this area and I divide every single term by 1/2 A times B times C, okay, I'm going to end up with an equation. Since these are all equal to each other, when I divide, let's just look at this first term. When I divide this by 1/2 A times B times C, well, the 1/2, the B, and the C cancel, and we're left with little a in the denominator. So we have sine of A over little a. And of course, that's equal to this term, which when then we've divided by 1/2 A times B times C. Well, the 1/2 A and B cancel, and you're left with 1 over C. And similarly with this one, when you divide this by 1/2 A times B times C, well, the 1/2, the A and the C cancel, and you're left with a 1 over B. So we have sine of B over B. Okay? So this, what you're looking at right here, is the law of sines. It gives you a relationship between any combination of an angle and its opposite side and another angle and its opposite side. Okay, so, and you could also do, I think maybe the book does it upside down. So you have A over sine A, B over sine B, C over sine C. It really doesn't matter, because as long as sine of C is not 0, then it works, right? Because sine of 0 will be 0. You can't have 0 in the denominator. But think about what that would mean for a triangle. That means that the angle has to be either the angle in question has to either be 0 or 180, which isn't a triangle. So it all works out consistently. So, all right. So what does this do then? Okay. So what I'd like to do is I'd like to sort of again diagram how we solve the two different kinds that we have. So we have we have angle, side, angle, and then we have angle, angle, side. So let me just start with angle, angle, side. So consider this, maybe we'll use an obtuse triangle now. So let's say that I know one of the angles, let's call it, let's again give it some labels. How about A, B, C, little a, little b. So suppose we know, so in order to do angle, angle, side, I need two angles. Let's suppose we know angle A and B, and then we need one side that's not included. So how about B, little b? All right, so if you knew these, the strategy would be to first find C. Now, how do we do that? Well, we know A plus B plus C is equal to 180 degrees. And since we we know A and B, it's pretty simple to find C, right? Now, once we've found C, we now have all three angles, and we will solve the following equations. So we're going to use sine of B over B equals sine of A over A, find little a, right? And why is that? Well, because we know A, capital B, and little b, we know this quantity, sine of B is easily known. We have this length, we have that angle, so therefore we have the sine of that angle, and then A is the quantity we don't have. So we do the little bit of algebra, rearrange this so that you're solving A equal blah, 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 blah. And then finally, we do sine of B over B equal sine of C over C. And again, because in the first step we found C, we can now do the same trick that we did here in step 2, rearrange this, solve for the length C. That's the strategy for doing an angle side problem. Now be careful, because this right here is actually a calculation. And because it's a calculation, it's susceptible to the rules for significant digits. So you're using a number here that you've calculated already. It does, in this case, honestly, it won't make any difference as long as you use, I mean, if for some reason, if the angles had different positions for significant digits, like maybe one angle was measured to one level of accuracy and one's to another, there could be some subtleties here. You're going to use the calculated value for C, but you're going to report the value that's based on significant digits. In almost, I think, every problem that's in the textbook, those happen to be the same thing, because they don't improve or decrease the accuracy of one angle over the other, but it could happen. So just be cognizant of it. You're actually using a number that's been calculated in a later calculation. Make sure you use the calculated number, not the approximated number. Okay, so let's look at an example and try to solve it. So angle side. Let's say that suppose A equals let me find one here. Okay, so 22 degrees. B equals 95 degrees, and A is equal to 42. Now I switch, you know what, just to make it simple, let me make it B, so it's exactly the same sort of setup. Okay, so A, B, and B. All right, so first, C is equal to 180 degrees minus A minus B, which happens to equal 180 degrees minus 22 degrees minus 95 degrees. And if you don't trust your arithmetic, I mean, it's perfectly reasonable to pull out a calculator. 180 minus 22 minus 95 gives you a number of 63 degrees. So we have 63 degrees, okay? And we don't need to do any, apply any significant digits, because the digit of significance is at the degree anyway. So like I said, this is a situation where it's not going to make any difference. So now we have the value of C. Let's now try to find these others. And this is where the algebra gets a little bit trickier, but it's not too bad. Okay, so second one, remember we're going to now find side A. So side A, the governing equation here is sine of B over B equals sine of A over A. Find A. So to solve for A, we're going to, I'm going to basically multiply both sides by A, multiply both sides by B, divide both sides by sine of B. You're going to end up with an equation, a little bit of algebra here. I expect you could probably do that. A is equal to B times the ratio sine of A over sine of B, okay? and the values that are associated with it. So B was 42. Yeah, 42. And you know what? I mean, we don't have any units on this. That's fine. Normally they do have units like centimeters, inches, feet, something like that. We might, let's just leave it unitless for now. So let's see, A was 22 degrees and B was 95 degrees. So calculating this, we have sine of 22 divided by sine of 95, and then times the distance, 42. We have 15.793576, etc. Now we will approximate that in the end, or we'll round it using the rules for significant digits. But for now, we'll just leave it at that. And rather than do all the same, I mean, we start with a very, very similar formula. We're going to end up with one that is very similar as well. To find C, C is equal to, again, B times sine of C over sine of B, which we have 42 times the sine of 22. And as you recall, C was 63 degrees, so sine of 63 degrees. So 22 times sine of 22 divided by sine of 63, and then times 42, we have 17.65809, whatever. Okay, so when we now sort of finish the problem here, A is equal to 22, that was given. B is equal to 95, that was given. C is equal to 63, that was calculated in the first step. A was calculated, apply two significant digits, because everything going into this problem has two significant digits, right? 42, 22, 95. So the best we can hope to get out of it, because it's a product, is two significant digits. So this is 16, and B was given in the problem as 42, and C then was calculated right here in this last step here as 18. So there is our solution with an appropriate number of significant digits. Now it may feel a little bit uncomfortable to round this to 18, but again, the rules for significant digits say that this is what we're supposed to do. Like I said, for whatever reason, when this digit is like 4, 5, or 6, people for some reason don't really want to round it, but that is exactly what you're supposed to do. This one, for some reason, is much more appetizing, easier to pull off. But anyway, so there's a angle side. Video's getting a little bit long, so I will come back and I will then do maybe a couple more to sort of hammer this home. So I will see